Okay, in this video I want to talk about eigenvectors and diagonalizability a little bit more. So I'm going to look at this particular example, find the standard matrix for a linear transformation given by we know what t does to three particular vectors. If you stare at these three, they're all actually eigenvectors. T of this vector is a multiple of the original vector, and so the eigenvalue would be 1. T of 1, 0, 1 is a multiple of 1, 0, 1. It's actually 2 times the original. And T of 1, 1, 1 is a multiple of the original. It's actually 5 times the original. So each of these is an eigenvector. And so it's natural to think about, instead of finding the standard matrix, why don't we start by talking about the matrix for T relative to this basis of 3 eigenvectors. So we have two different bases in mind. We have the standard basis that eventually we'd like to find our standard matrix relative to the standard basis, and then we have this basis of eigenvectors. So let's investigate these eigenvectors a little bit more. If I take T of the first vector, the first eigenvector, then I get 1, 2, 4, and I'm going to write that as a linear combination of vectors in B prime, which is 1 times 1, 2, 4 plus 0 times 1, 0, 1 plus 0 times 1, 1, 1. Okay, so that means that T of 1, 2, 4, if we write its coordinate vector relative to the B prime basis, so B prime vector relative to B prime basis, what we're going to get is our coefficients, 1, 0, and 0. Do the same thing for each of the other eigenvectors. T of 1, 0, 1 would be 2, 0, 2. We want to write that as a linear combination of 1, 2, 4, 1, 0, 1, and 1, 1, 1. But we should be able to see right away at least one solution. Turns out it's the only solution, which is double the middle vector. And so T of 1, 0, 1 relative to the B prime basis would be the coefficients that we see, 0, 2, and 0. And finally, T of 1, 1, 1 would be 5, 5, 5, which is, again, going to be a pretty simple linear combination of the B prime vectors, because we know it's 5 times the 1 in the end. And so we just need zeros as our other coefficients. So T of 1, 1, 1 relative to the B prime basis is going to be these coefficients, 0, 0, and 5. Okay, so we haven't found the standard matrix, but we have found the matrix relative to the B prime basis. So I'm going to call this A prime, which has columns, these 3 vectors. So 1, 0, 0, 0, 2, 0, and 0, 0, 5. Okay, let's slide the page up a little bit. And now we want to see how is this A prime matrix actually related to the standard matrix, which should be relating back to the original basis B. So let's think back to the previous video about how we would change a basis. So the relationship between A and A prime is given by, you put p's on both sides. I don't know if this is necessarily the most convenient way for me to write it. No, you know what, let's switch. Let's put the A prime there since we actually know A prime. So we need to have a matching basis on the inside and the basis we want to end up in on the outside. So we're going to need to find the two transition matrices PB B prime or P B prime B. Okay, so let's see. Let's just pick one of them. Our strategy for finding a transition matrix was to put B and B prime next to each other, and the matrix for B and the matrix for B prime next to each other. So let's try that. The matrix for B, just writing the vectors of B as columns, would be 1, 0, 0, 0, 1, 0, 0, 0, 1. The matrix for B prime would be 1, 2, 4, 1, 0, 1, and 1, 1, 1. Okay, So think about which way is it going to be more easy to put these two, because our strategy was if you put one b on the left and the other b on the right, when you row reduce, you should end up with an identity on the left and a p on the right. Obviously, this one on the left is going to be easier to row reduce. If that's not obvious, wait until I write it down, and then it will become more obvious. Now, I say this is the easier one to row reduce because it's already been row reduced. You can't do anything else. It's done. If I had put b prime and b in the other order, that'd be annoying. I'd have to actually row reduce it. This one is actually done. It's already in the form identity and then a p, and the order of the b's is the same as the order over there. So b on the left, b prime on the right. So that means that this matrix here with eigenvectors as columns is actually that matrix. And also, so let's write that formula down one more time, and then I'll get rid of the previous piece of paper. Okay. So we noticed that the A prime matrix was a diagonal. We noticed that this matrix on the left has eigenvectors as columns. That's the matrix P. That one over there. So I'm going to call this C. And it has eigenvectors as columns. The diagonal has eigenvalues on the diagonal. And this other matrix, well, it's the transformation that undoes whatever C did. So this is actually just going to be C inverse. And so if I write all that down, it should actually look familiar because we've seen it before, AC/DC formula, for the relationship between a matrix and its similar diagonal matrix. Okay, so that means if we actually want to find A, one way to do it, this is not the only way, would be to actually plug in what all these things are. So our matrix C is that, our matrix D is 1, 2, and 5 on the diagonal, and our matrix C inverse, I'm just going to write as 1, 1, 1, 2, 0, 1, 4, 1, 1 inverse. So I'm going to type this in a calculator, and then it should tell me what the matrix A is. Okay, I typed it in a calculator, and this is the matrix I got. If you wanted to check your answer, the best way to do that would be to go back all the way to the original definition of T. T of 1, 2, 4 is equal to 1, 2, 4. Take this matrix, multiply it by 1, 2, 4, see if you actually get 1, 2, 4, and so on for the other two. But I just wanted to try and connect the two ways we've written this. We did it in 5.2 using transition matrices. We did it in 5.3 like a month and a half ago using the matrix C, which is a similarity transform.